Hello everyone. In the first video, we talked about the Laplace transform and some examples. And in the second video, we talked about the inverse Laplace transform and we solved several examples. In this video, we will be talking about the properties of Laplace transform and some of its application. The first property, we will talk about linearity. So you can think of Laplace transform as a system that transforms a signal in the time domain to its Laplace domain, which is the frequency domain. And this is the definition of the Laplace transform. So I can go from x of t to x of s and do the inverse Laplace transform and go back to x of t. So linearity basically says if you have a signal and it's x1 of t, and the Laplace transform is x1 of s. Now what happened if I multiply the signal in the time domain by a? Then the Laplace transform of this one will be the same x1 of s multiplied by the same a. A could be an amplification constant. So that's one condition for linearity. The second condition is the following. Let's assume you have a second signal x2 of t and the Laplace transform is x2 of s. Now let's generate a new signal that consists of a linear sum of x1 of t multiplied by a plus x2 of t multiplied by b. Then what's the Laplace transform of this new signal? It will be just the sum of x1 of s, which is this one, and x2 of s time b. And linearity is very important concept that help us simplify the analysis of input and output to a system. So if I have a very complex input, I can break it down to simple inputs, and then I can find the Laplace transform for this one by itself and this one, and the sum will be the Laplace transform of this complex signal if I add them together. And we will see an example where we demonstrate how to use linearity. The second property is time shifting property. So if I have a signal x of t and this is the Laplace transform x of s, what happened if I shift the signal in the time domain? So the signal might be this one, x of t. Now I shift it by this amount. Then the Laplace transform of this shifted signal will be exactly of the original signal time e minus t0 s. And this is just a phase shift in the frequency domain. Now remember, s is sigma plus j omega. So this is, you can think of it the same as if x of t is cosine omega 0 t. Now shifting in the time domain, that means it would be cosine omega 0 t minus t0. So this is just cosine omega 0 t minus omega 0 t0. That's a phase shift. And we can prove this by starting with the definition of the Laplace transform. So x of s equal minus infinity to infinity x of t e minus s of t. Now if I want to find the Laplace transform of a shifted version, then I just multiply this by e minus s of t dt. Now let's define tau to be t minus t0. So d tau will be dt. So now this integral will become, when t goes to infinity, tau will go to infinity. So that's here. When t go to minus infinity, tau will also go minus infinity. t0 will have no impact. Now this will be x of tau e minus s. Now replace this t by what is equal from this equation. From here is just tau plus t0 equal t. So that will be tau plus t0. And dt here is just the same as d tau. And this will be, now minus s times t0 has nothing to do with the integration variable tau. So I can take it outside the integral as e minus s t0. Now when you look at this integral, I can substitute for tau t again, and then this integral is just the Laplace transform of the function x. So that will be just e minus s t0 x of s. And that's this one. So the Laplace transform of a signal shifted in the time domain is just the same Laplace x of s phase shifted by t0. Now many of the property, we just follow the same step here, but I'm not going through the proof. You can find it in the textbook. It's straightforward, and there are many videos that show each property and the proof. Here I will try to demonstrate the meaning of it and examples. Now, if the signal is causal signal, like start at t equals 0, then time shifting, if that is the signal in the time domain, and this is the Laplace transform x of s, if I shift the signal by t0, then that would be this one. And later on, we have to be very careful. X of t minus t0, u of t, is not the same as this. Later on, we will see. Let's take an example that demonstrates time shifting and linearity. So we have this signal x of t, and we need to find the Laplace transform x of s. Now, one way to do this is to break this signal x of t as a linear sum of two simple signals, x1 of t and x2 of t. So we can write x of t equal x1 of t plus x2 of t. Now I have to express this x1 of t first. Well, this line, which is t minus 1, but it exists only from 1 to 2. So then I can multiply it by a pulse, which consists of this unit step function, start at t minus 1 and subtract from it another unit step function, start at t minus 2. So if I plot this one here, this just looks like this, and you subtract from it u of t minus 2. When I add these two, I get this pulse. Now, this is this pulse here. When you multiply it by this line, t minus 1, you will only get this, because then everything here will be 0, and everything here will be 0. So you will not get this dotted here and this. All right, so that is our first signal, t minus 1, u of t minus 1, plus. Now x2 of t is only this one, that one here, this pulse. So that will be u of t minus 2 minus u of t minus 4. So this unit step function, and you subtract from it this, you will get only this pulse, which is this. Okay, let's just keep multiplying. So this will be t minus 1 Now I can use the table to find the Laplace transform of this one, which we have in the table, the Laplace transform of t u of t, 1 over s squared. Then we can use the time shift property, and the Laplace transform of this one can be found. But we have a problem here. If I think of this as x of t, it's shifted by 1 unit, but this unit step shifted by 2 units. And in the time shifting property, both the signal and the unit step has to be shifted by the same amount to use the time shifting property. So we can use a simple trick here and do the following. Just to have here minus 2, I will subtract 1 and add 1. So that means I do minus 1, that will be minus 2. But then I have to add 1 here. So this is the same. Minus 2 plus 1 is just minus 1, the same as here. Plus u of t minus 2 minus u of t minus 4. Okay, now this will be just t minus 1. And here I will break it. I will break it to t minus 2 times this, and I will get t minus 2 times u of t minus 2. Then the 1 times this, I will get minus 1 u of t minus 2. plus u of t minus 2 minus u of t minus 4. Now I can use the shifting property, t minus 1, or let's make it general, t0, u of t minus t0. The Laplace is 1 over s squared e minus st0. Now the Laplace transform of this one will be tu of t is 1 over s squared, and it's shifted 1 unit, so that will be e minus s1 minus this one is tu of t, which is minus 1 over s squared, and shifted 2 units, so that's e minus 2s, using this shifting property. This minus u of t minus 2 and this plus will cancel, then minus. Here I have u of t shifted 4 unit, so from the table u of t, the Laplace transform is 1 over s, and it's shifted 4 units, so that will be e minus 4s. And that's the answer. So here we use linearity because we broke the signal to x1 and x2, so the Laplace transform of this one is just the sum of the Laplace transform of this one and this one. And we use time shifting property to find the Laplace transform this and this one from the table. Let's move now to the frequency shifting property. If I have a signal x of t in the time domain and the Laplace transform is x of s, now if I multiply this x of t by this exponential, es0t, in the frequency domain, it means I shifted the spectrum of this one to be centered around s0. For example, let's say I have this simple pulse signal x of t. If I do the Laplace transform, I will get this surface centered around 0, sigma 0, omega 0 here. Now, if I multiply these by es0t, which is like multiplied by a sinusoidal with some decay, and I try to find the new spectrum, it will be exactly the same here, but it will be shifted around s0. So instead of the center at the origin, now the centered around s0. And s0 is just sigma 0 and omega 0. When we come to the frequency domain, we will use this property in modulation. But let's take an example to demonstrate the frequency shifting property. So we have a signal and we need to find the Laplace transform. Well, from the table, I have the Laplace transform of this signal. S over s squared plus b squared. Now, I multiply this signal x of t, let's call this x of t, by e minus a of t. So according to the frequency shifting property, this will be x of s minus a, because s0 is just minus a. So that is just x s plus a. So this is x of s. So wherever I see s, I replace it by s plus a. So then this will equal s plus a over, here is s, so that would be s plus a squared plus b squared. And that's the answer. Let's look at another important property, which is the time differentiation property. We use this property in solving differential equation of a system. So if I have a signal x of t and the Laplace transform is x of s, now if you differentiate this signal in the time domain, then the spectrum or the Laplace of this signal will be exactly the same here, multiplied by s, and subtract from it the initial value of the signal in the time domain, right before 0. You can think of it this way. Let's say we have a signal x of t equal a sine omega 0 t, and the plot something like this. And the period here, let's say 1 millisecond. So now I can think of this signal in the time domain and say it's a sinusoidal with amplitude a and a period 1 millisecond. Or I can think of it in the Laplace domain or frequency domain, which is the same as frequency domain, and think of it This is a sinusoidal signal with frequency 1000 Hertz and the strength A. So now if I take the derivative of this one, now if I think of the Laplace domain of this one, it is still a sinusoidal, but now the amplitude is multiplied by omega 0. And there was a phase shift from sine become cosine. So this is what you can think of as S here. Except instead of sigma plus j omega 0, sigma here is 0. Because it's sinusoidal, it doesn't decay. And that will be the S. Now, what is this component here? Let's take another signal. Let's say this is the x of t. Let's plot it here. If this signal exists before t equals 0, then this part here is the value of the signal right before 0. Right before 0. So something like this, the value of this signal here. Now, what if I take the second derivative? So now I take the second derivative of this one. It will be now omega 0 square a sine omega 0. So now we have here s squared. And the initial conditions, again, it will be minus s, which is the frequency. In the Laplace, this frequency could be complex, decay rate and oscillation rate, time the signal right before 0, which is this one, minus the derivative of the signal evaluated at 0 negative, right before 0. So that will be like this derivative here, the slope, whatever that slope, evaluated at t equal 0 or before 0. Now, if the signal is causal, like something like this, then all these initial conditions will be 0. In system analysis, we said energy stored in the system will be 0. You can go to a third derivative, or fourth derivative, fifth derivative, and this is the general equation for n derivative. You don't have to memorize this equation because there is a pattern. For example, let's look at this pattern. So if I want to find the third derivative, automatically the derivative, if n is the order of the derivative 3, then the Laplace domain of this will be s cubed x of s. Everything else now will be just initial conditions. I will have here minus s to the power of 2, 1 less than this, minus s to the power of 1, minus s to the power of 0. And here you will have the initial condition, the first one. The second one will be the derivative. The following will be the second derivative. Now s to the power of 0 is just 1. So this is 1. And this is exactly the same as this one. And if you have fourth derivative, you will just have the Laplace transform s to the power 4x of s, and then I will have minus s cubed minus s squared minus s to the power of 0. And here I will have x0, first derivative, second derivative, third derivative. The next property is the frequency differentiation property, which is taking the derivative of x of s in the Laplace domain. So if I have a signal x of t and then multiply it by t, then the Laplace transform of this one will be just x of s, the Laplace transform of x of t, taking the derivative of it in the Laplace domain. And when we take the derivative of anything, basically you want to know the rate of change of this object you are taking derivative of. So when we take the derivative in the frequency domain, that means I am interested to know how the frequencies fluctuated, how the sound fluctuates from 10 Hertz to 20 Hertz to 5000 Hertz. That fluctuation, I want to see it in the frequency domain. So I can take x of t and multiply it by t, then take the Laplace transform, and that will reveal this information. Or I can take x of s and take the derivative with respect to s. One way to see this one is the following. If you have a signal x of t, which is a unit step function like this, now if I multiply it by t, which is a function like this one, now the signal will be this one, t u of t. The Laplace transform of this one, the u of t, is 1 over s. Now what's the Laplace transform of this one? It will be, according to here, minus the derivative of x of s. The derivative of 1 over s with respect to s is just minus 1 over s squared. So that is 1 over s squared. So if you look in the table, that will be the Laplace transform of this signal. If we plot it to see what it means, now the spectrum here, I will draw it in blue, so it will look something like this. The magnitude looks like this. Now if I draw the spectrum of this one, the magnitude, it will be decaying at faster rate. So that means this one has less frequency component than this one. And how could that be? Well, I can actually see it here, because see, the u of t, it's 0, 0, 0, that's sudden jump. That sudden jump creates a lot of frequency, and that will be this blue surface. But tu of t, it's 0, 0, 0, then a gradual increase, so less frequency, and that will be this red surface. Okay, let's take an example. I have this signal, and we need to find the Laplace transform of this signal. And there are different ways to solve it. One way is, if I can make this signal simple, such that in the time domain it's so simple I can find the Laplace transform, that will be great. Well, that's one way. So then I can realize if I take the derivative of this x of t, it will be simplified enough to use the table. So the equation of this line is just t. So the derivative of t is just 1. So that's 1 here. The equation of this line, the slope is minus 2. It's just this amplitude 2 divided by this width 1. So that's minus 2. And it's shifted 3 units to the right. So that will be t minus 3. Now if I take the derivative of this one, it will be just minus 2, which is here. And it will be minus 2 until that point, 3, and then it's 0. Good. So now x of t, let me enlarge these. Now x of t is dx of t. Well, I think I can differentiate it again to simplify the signal even more. So if I take the second derivative now, well, this is 0, 0, then a sudden jump. So that will give me an impulse of amplitude 1 because it jumped 1. Then that's a DC. So the derivative of a DC is just 0, no changes until it reached this point. Then it jumped down. How many units? 3 units. That's 1 unit. This is 2 units, 3 units. So I will get a unit impulse here of a strength minus 3. Then that's a DC. So the derivative is 0. Then a sudden jump up. How many units? 2 units. So I get this impulse. Okay, so now I have this signal. Let me write it here. d square x dt square equal this impulse, which is plus this impulse at 2, and the amplitude is minus 3, so that's minus 3, and impulse at minus 2, plus this impulse of strength 2 at t minus 3. But the question was, find the Laplace transform of x of t. I need to find x of s. That's what I need to find, the Laplace transform of this function. Well, now I can use the derivative property. Let's clean up this. So I will take the Laplace transform of this equation. So the Laplace transform, I use the differential property. This will be just s square x of s minus the Laplace transform of this impulse is just 1. The Laplace transform of this impulse shifted 2 units. That will be just minus 3 e minus 2s plus the Laplace transform of this one again 2 times 1 shifted by 3 units. Now this will be s square x of s. Now, what is the value of this function at t before 0? Well, this is the function x of t. So here it's just 0. So that will be minus 0. What's the derivative of the function at t 0 negative? That means the derivative of this is just 0. This signal is causal. So at t equals 0 is just 0. Equal 1 minus 3e minus 2s. And finally, we are after x of s. So I divide everything here by s squared. So I get x of s equal 1 over s squared minus 3 over s squared plus 2 over s squared. And this is the answer. Using the property, the solution of this problem becomes very easy. But the most important use of the derivative property is system analysis, which will be the next video. Okay. The next property is time integration property. So if I have x of t and I have the spectrum x of s, now if I take the integral of the signal in the time domain, so I have x of t here, if I integrate it, then the resulted signal will have a spectrum that looks exactly the same here, divided by s. And if I give you, for example, cosine omega 0t dt, if I integrate this, it will be 1 over omega 0 sine omega 0t. So the spectrum of this one, you can think of it, is the same as the spectrum of these. The sine and cosine, they are just phase shifted by 90 degrees, but it's divided by omega 0. So the spectrum of the integral will be the same as this spectrum, but divided by its frequency, or s. In this case is omega 0. Now, when we think of system design, because when we build a system to process a signal, usually the signal has noise, and noise has high frequency component. So if I use integration instead of differentiation, look at the spectrum with the noise will be divided by its frequency, s, and s for noise usually very high. So the noise will be attenuated by integration. And when we do system design, we will see that it's better to use integrator instead of differentiator. Now, if you divide the signal x of t in the time domain by t, then the Laplace transform of this signal will be just the integral of x of s. So it will be the Laplace transform of this one integrated. We will be using this property when we do system design. Okay, the next property is scaling property, and scaling is compressing or expansion. So you have a signal in the time x of t, and that's the Laplace transform x of s. If I scale the signal, like if I compress it in the time domain, in the Laplace domain, it will be the opposite, expansion. So compression in the time domain by a factor of a is expansion in the Laplace domain by a factor of a. Expansion by a factor of a in the time domain means compression by a factor of a in the Laplace domain. So for example, let's say you have this pulse x of t, and let's say this is the Laplace x of s. Now, if I expand this pulse by a factor of 2 here, then the Laplace transform of this pulse will be 1 over a x of s over a. It will be exactly this one, except it's compressed by a factor of 2. So if that was like 4 omega, omega is 4, this will be 2. And the amplitude actually will be larger, because here a is 0.5, so 1 over 0.5 is 2. So if that was 1, this will be 2. If sigma here is 2, this will be 1. So here in the time domain, x of t, we expand it. In the frequency domain, this is compressed. The next property is convolution, and that is another important property we will use in system analysis. If I have an input, or call it x of t, and x of s is the Laplace transform, and I have another signal h of t, let's call it the impulse response of the system, then the Laplace transform, we call it h of s. Now convolution in the time domain means multiplication in the Laplace domain. So you just multiply x of s times h of s. The signal here, let's call it y of t. Now in the frequency domain, that will be y of s. And I can get it just by multiplying x of s times h of s. Now multiplication in the time domain is convolution in the Laplace domain. Some of the property we are not doing examples because we will be using them in system analysis. Here we are just introducing them. For example, here, this is the convolution that we use it for system analysis. If I have a signal input x of t and I have a system with impulse response h of t, we know in the time domain analysis I can find the output y of t just by carrying out this convolution. And this we did it in chapter 2. And we call this y of t the zero state response, because it's the response due to the input, and all initial conditions in the system is zero, no energy stored. So that is just the zero state response, the system response to the input. So now let's look at the Laplace domain. If we do the same analysis but in the Laplace domain. So this will be just x of s, that's the input. Take the Laplace transform of h of t, you will get h of s. So the output y of s will be just the multiplication, the input times h of s. And that y of s, again, the zero state response. Now, if I need to find the transfer function h of s from this equation, I will get h of s equal y of s divided by x of s, which is this. And h of s here, we call it the transfer function of the system. Basically, it transfers the input to the output. So let's take an example of the convolution property. So you can think of these as x of t, the input, and this as h of t, the impulse response, and you get y of t. And we can carry out this convolution in the time domain, or we can just find y of s in the Laplace domain. So that will be just x of s, h of s. From the table, we can find the Laplace transform of this one, and this is just 1 over s minus a, and h of s, the Laplace from the table, is just 1 over s minus b. So this is s minus a, s minus b, 1. So that's y of s, but I don't need y of s, I need y of t. So we do partial fraction expansion, and y of s will be equal c1 over s minus a plus c2 over s minus b. And we need to find c1 and c2, and we can do this one, c1, as we did in the previous video. I multiply everything by s minus a, and I set s to equal a. So that will be 1 over s minus b, s equal a. So that is 1 over a minus b. Same thing, c2. I multiply everything by the denominator of c2, which is s minus b, and I set s to equal b. So I have here 1 over s minus a, s equal b, that is 1 over b minus a. So y of s equal 1 over a minus b divided by s minus a plus 1 over b minus a divided by s minus b. And now I can use the table and find the Laplace transform of this one. Y of t is 1 over a minus b, that's just a constant, e a of t plus 1 over b minus a, e b of t. And everything here multiplied by the unit step function because it's a causal signal. And I can take 1 over a minus b as a common factor. So this will be e a of t. This will be minus e B of t, U of t. And that's the answer. So the convolution of this is the answer. Well, this is all the property we discussed. This is the table. You can always use it to simplify system analysis or system design. Next video, we will demonstrate how do we use Laplace transform to solve differential equation and system analysis, which is a very powerful tool. Thank you for watching and see you soon in the next video.